Welcome to the next session of Subject Engineering Maths. Now, we were in chapter 7, that is numerical methods. In the last session, we have finished Newton-Raphson method. Now we go for, in this session, we discuss bisection method, regular falsity method and secant methods. Now, for the next two methods, that is bisection and regular falsity method, the prerequisite, as we mentioned in the last lecture, is intermediate value theorem. What intermediate value theorem states? If f of x is a function which is continuous in closed interval a comma b and function takes opposite signs at the endpoints, then the function has the equation f of x equal to 0 has at least one root in open interval a comma b. See, we have a function f of x equal to, this is my equation, f of x equal to 0. Now I need to find the root of this equation. See, what is my task is, before finding the root of this equation, I must have some assurance that root belongs to specific interval, right? If I guess that root belongs to this interval, then I may go for approximations. So therefore, here my interval is closed interval a comma b. Assume that this is a function which is continuous in closed interval a comma b and f of a dot f of b is less than 0. So that means this can be negative. In that case, this must be positive. If it is positive, this must be two negative. Only two cases. So f of a, if it is negative, then this must be positive. If it is positive, then this must be negative. Since the graph is continuous and function takes opposite signs at the endpoints, the graph must cross through x-axis at least one time in open interval a comma b. And that crossing point is called the root of this equation f of x equal to 0. In fact, this is called intermediate value theorem. Now, in fact, this is the base for the next two methods, bisection and regular falsity methods. Now, let us start with the session with bisection method. That is method number 2 to solve algebraic and transcendental equations. Bisection method. Suppose we have a function f of x which is continuous in closed interval a comma b and function takes opposite signs at the endpoints. That is f of a dot f of b less than 0. Then the equation f of x equal to 0 has at least one root in open interval a comma b. So therefore, by this theorem, there is a confirmation that root belongs to open interval a comma b. So when root belongs to open interval a comma b, then I start with iteration number 1. So therefore, here the value of root in first iteration, x1 represents the value of root in first iteration, and this is given by a plus b divided by 2. So here x1 is a plus b divided by 2. This is nothing but, we are guessing actually. This is nothing but value of root in first iteration. So here x1 represents value of root in first iteration. x1 equal to a plus b by 2. Midpoint. That's why it is called bisection. So we are dividing an interval a comma b into two subintervals exactly at its midpoint. So therefore, the representation will be like this. This is a comma b. So at this point, the level x1 equal to a plus b by 2. Now immediately, if I calculate x1 equal to a plus b by 2, here I am guessing it may be root of the equation. Immediately I go for f of x1. So if f of x1 equal to 0 implies x1 is a root of f of x equal to 0. So then in that case my task is over. So x1 is a plus b by 2. This is value of root in first iteration. So immediately I am checking whether x1 is a root or not. If f of x1 is 0, then it confirms me that x1 is a root of the equation. My job is over. Otherwise, I can go for step number 2. That means root may lie in the left subinterval or right subinterval. That means divide this interval into two equal subintervals at its midpoint. This is a comma x1 and this is x1 comma b. Let us see. Here I said that f of a dot f of b less than 0. So we have two possible cases. If it is negative, this must be positive. If it is positive, this must be negative. Now I assume that f of A is less than 0 and f of B is greater than 0. So in that case, here I assumed that x1 is a plus b by 2. If it is a root, then my job is over. Otherwise, root may belong to either this interval or this interval, because I know that root belongs to this interval. But suppose if x1 is not a root, then root may fall in the left subinterval or right subinterval. So that depends on some condition. Let me tell you that. So here f of a less than 0, f of b greater than 0. Here otherwise means x1 is not a root. That means f of x1 can be greater than 0 or less than 0. Suppose if f of x1 is greater than 0, implies root lies in open interval a comma x1, because f of a is less than 0. Here my assumption is f of x1 greater than 0. So function takes opposite signs at the endpoints. Therefore definitely root must belong to this left subinterval. So whenever f of x1 greater than 0 implies root lies in open interval a comma x1, and the value of root in second iteration, that is denoted by x2, and that is given by a plus x1 divided by 2. So this is the value of the root in second iteration, a plus x1 by 2. If f of x1 is less than 0, so already f of b is greater than 0. This is our assumption. If f of x1 less than 0, then root belongs to this interval. So whenever f of x1 is less than 0, implies root lies in open interval x1 comma b, and in this case the value of root x2 equal to midpoint of right subinterval, that is x1 plus b divided by 2. So therefore whenever root belongs to this interval, in this case x2 becomes a plus x1 by 2. If root belongs to this interval, then x2 becomes x1 plus b by 2. So like this frequently we divide the interval into finite number of subintervals at its midpoint until we get the root of this equation. So this we call it as bisection method. This is called bisection method. See, this is exactly similar to one general problem. Suppose I have 16 1 rupee coins. 16 1 rupee coins. Assume that 15 1 rupee coins have same weight, and one coin have different weight. One coin has different weight. So now, but all are mixed. All look like same. I have 16 1 rupee coins. Among those 16, 15 1 rupee coins have same weight, and one of the remaining coin has different weight. It may slightly decrease, slightly low or slightly high, but all look like very same. Then I need to identify the coin having different weight. So in that case, I have a pawn weighing machine. So in that case, let us mix all 16 coins. So therefore, what I will do is divide this 16 1 rupee coins into two groups: 8 1 rupee coins, 8 1 rupee coins. So therefore, weigh all these coins. So 8 on one side, 8 on one side. So therefore, you can easily guess. Suppose if the leftmost 8 coins are going down and the rightmost 8 coins are going up, that means what is it? Suppose if it has slight height weight, for example, this has more weight, for example. So 15 1 rupee coins have same weight, for example 0.5 grams. So the weightage in this case is 0.5 grams. In this case, for example, this is 0.55 grams, for example. Say, now I need to identify this faulty coin. That means the coin having more weight compared to remaining coins. So in that case, divide these 16 coins into two groups. 8 8 8. You don't know where this coin belongs, either leftmost or rightmost. Then take a weighing machine. So 8 are in the left hand side, 8 are on the right hand side. So if a LHS part, left hand side part, is going down, that means the coin having more weight belongs to leftmost. Then I will choose like this. But still I didn't find this. Again, divide this into 4 4. Again go through weighing machine. Suppose if the RHS part going down, then the coin having highest weight belongs to this RHS part. Then again do this, divide into 2 coins. Suppose if this goes down, the coin having more weight belongs to this. Okay. So in this case, it belongs to like this. Now it divide this into 1 1. Suppose if it goes down, then this is exactly faulty coin. See, what is happening in this case is, this is one comparison, second comparison, third comparison, fourth comparison. So therefore, when you take a 16 coins, so within 4 iterations, you can easily guess what is that the coin having more weight or slight weight. So 4 comparisons. That means here the number of coins is n, this is 16. Basically, so we can easily find this in terms of 4 iterations. At most, this is 2 power 4. That means if the value of n is 2 power k, because this is 2 power 4, so we are getting the faulty coin within 4 iterations at most. So if n equal to 2 power k, then we can get easily in terms of k iterations, that is nothing but log n to the base 2. So this is the most effective result for bisection method. So this is just like binary search method. So whenever you want to search an element in the array of n number of elements, array means elements are arranged in increasing order or decreasing order, then I choose at first the starting element. If my element is matched with, for example, middle element, then my job is over. Otherwise, it may belong to either LHS or right hand side. So based on that, so it is exactly like this bisection method. There we were saying number of coins 16, 8, 8, 2 groups, 4, 4, 2 groups like this. Here the interval is dividing into 2 equal subintervals at its midpoint. So we repeat this process until we get root of the equation. So this method is called a bisection method. So remember always one point, all these iterative methods are not perfect methods, they are approximation. Sometimes for particular examples they may work absolutely right, sometimes they may go slightly errors may be complicated or error may be very close to 0, right? So note these points. Bisection method, this is second iterative method to solve algebraic and transcendental equations. Let f of x be a function, let f of x be a function which is continuous, let f of x be a function which is continuous in closed interval a comma b, and f of a comma f of b have opposite signs. Let f of x be a function which is continuous in closed interval a comma b, and f of a comma f of b have opposite signs. Then f of x equal to 0 has at least one root. Then f of x equal to 0 has at least one root in open interval a comma b. I repeat once again, let f of x be a function which is continuous in closed interval a comma b, and f of a comma f of b have opposite signs. Then f of x equal to 0 has at least one root in open interval a comma b. Right? Now assume that f of a less than 0 and f of b greater than 0. Now assume that f of a less than 0 and f of b greater than 0. F of a less than 0 and f of b greater than 0. Step 1. Calculate the value of root in first iteration. Calculate the value of root in first iteration using the formula x1 equal to a plus b by 2. Calculate the value of root in first iteration using the formula x1 equal to a plus b divided by 2. If f of x1 equal to 0 implies x1 is a root of f of x equal to 0. Step 1 is calculate the value of root in first iteration using the formula x1 equal to a plus b by 2. If f of x1 equal to 0 implies x1 is a root of f of x equal to 0. Otherwise, step 2. If f of x1 greater than 0, if f of x1 greater than 0 implies root lies in open interval a comma x1, implies root lies in open interval a comma x1 and x2 equal to a plus x1 divided by 2, and x2 equal to a plus x1 divided by 2. In the step 2 itself, continue. If f of x1 less than 0, if f of x1 less than 0, implies root lies in open interval x1 comma b, implies root lies in open interval x1 comma b, and x2 equal to x1 plus b divided by 2, and x2 equal to x1 plus b divided by 2, where x2 is the value of root in second iteration, where x2 is the value of root in second iteration. Like this, the procedure is repeated. Like this, the procedure is repeated until a root is obtained. Like this, the procedure is repeated until a root is obtained by dividing interval into two equal subintervals, by dividing interval into two equal subintervals at its midpoint. Like this, the procedure is repeated by dividing interval into two equal subintervals at its midpoint. Hope you understand these points. That means what we are doing is, suppose if I get the bisection method in the third iteration, what does it mean is we have applied indirectly intermediate value theorems over three subintervals, right? So this is a process, continuous process of applying intermediate value theorem for various subintervals until to get the root of equation. Okay, so we can have this structure, Now this is end of bisection method. Now I will tell you one point. In case of Newton-Raphson method, initial approximation is required, but whereas in case of bisection method, it is not required. So directly iterations start from 1 onwards. Iteration 1, iteration 2, like this. x1 represents value of root in first iteration. x2 represents value of root in second iteration, like this. Okay. So always choose an interval where root belongs by applying intermediate value theorem. If you get confirmation that root belongs to particular interval, then make sure that the root is nothing but midpoint of that interval. Always root is midpoint of that interval. But I am saying that these are all approximations, our guessings only. They may not be right, absolutely right values. Okay. So next I go through regular falsy method. Now, actually this regular falsy method exactly follows intermediate value theorem. So it is exactly like bisection method, only the difference is the iterative values will change. So they differ in formula only, but the concept is exactly same. So we have a function f of x, which is continuous in closed interval a comma b. So that means, and f of a dot f of b less than 0. Then f of x equal to 0 has at least one root in open interval a comma b. So assume that f of a is less than 0 and f of b less than 0. So therefore in that case root belongs to open interval a comma b. Therefore here the value of root in first iteration is given by a into f of b minus b into f of a divided by f of b minus f of a. So whenever root belongs to open interval a comma b, the root will be like this: a times f of b minus b into f of a divided by f of b minus f of a. But it guarantees that it always belongs to this interval. It always belongs to this interval. So the procedure is same. Suppose if f of x1 is 0, then x1 is a root of this equation. Otherwise, if f of x1 greater than 0, root lies in open interval a comma x1, and in this case the value of x2 is a into f of x1 minus x1 into f of a divided by f of x1 minus f of a. So formula will be similar to like this. Procedure is exactly same. Now if f of x1 less than 0, root lies in open interval x1 comma b, and in this case the value of root x2 is, this is x1 into f of b minus b into f of x1 divided by f of b minus f of x1, like this. So like this the process is repeated until a root value is obtained. So this is again a continuous process of application of intermediate value theorem over subintervals until to get a root of the equation. So the structure will be exactly same, but formulas will be slightly different. So in this case, if root belongs to this interval, x1 is this, a into f of b minus b into f of a divided by f of b minus f of a. If root belongs to this interval, then x2 equal to a into f of x1 minus x1 into f of a divided by f of x1 minus f of a. If root belongs to this interval, then the value of x2 is x1 into f of b minus b into f of x1 divided by f of b minus f of x1. So like this we can repeat the process. So you can write in your own words, but only thing is you make changes in the formulas x1, x2 like this. Now fourth method is secant method. Basically this method is obtained by doing some changes in Newton-Raphson method. So that's why this method is also called as modified version of Newton-Raphson method. Modified version of NR method. Now let us see what are the modifications in the NR method. So we start with value of root in second iteration. Value of root in second iteration in Newton-Raphson method. That is given by a2 equal to a1 minus f of a1 divided by f dash of a1. So instead of using x notations, I am using a1, a2. This is value of root in the second iteration. a2 is a1 minus f of a1 by f dash of a1. Now here f dash of a1 is basically, it is a slope. Derivative means it is a slope. So in fact this is nothing but a slope of line joining the points. This is nothing but a slope of line joining the points a0 comma f of a0 comma a1 comma f of a1. So here a0 is initial approximation, a1 is the value of root in first iteration, this is value of the root in the second iteration. So this is called value of the second root in the Newton-Raphson method. In the denominator we have f dash of a1. We know that derivative represents slope. So therefore it is nothing but a slope of line joining the points a0 f of a0 and a1 f of a1. Now let us see what is the slope of line joining of these 2 points. Here f dash of a1 is, for example you can call it as, this is x1 y1, this is x2 y2. So the slope of line joining the points x1 y1 is y2 minus y1 by x2 minus x1. Let us apply the same. Then this becomes f of a1 minus f of a0 divided by a1 minus a0. So therefore if f dash of a1 is replaced by this, then this, the value of a2 becomes a1 minus f of a1 divided by this, f dash of a1 is replaced by this equation, f of a1 minus f of a0 divided by a1 minus a0. So therefore in this case the value of a2 is given by a1 minus, this is a1 minus a0 divided by f of a1 minus f of a0 into, this is nothing but f of a1. So this is the value of root in second iteration in case of secant method. Now that means in secant method, iterations start from 2 onwards. So therefore, if you want to get A3, you must know previous 2 iteration values. A1 and A2 are required for A3. A2 and A3 are required to get A4. So to get the current value, I must know previous 2 iteration values. Therefore, the value of root in k plus 1th iteration using regular false, this is secant method. AK plus 1 is, if it is AK plus 1, this becomes AK. So this is AK minus, this is AK minus, this becomes AK minus 1 divided by f of AK minus f of AK minus 1 into f of AK. So therefore, this is the value of root in k plus 1th iteration in case of secant method. So here k values are starting from 1 onwards, 1, 2, 3, etc. So these are the modifications we can expect in case of Newton-Raphson method. To get another method, this is called a secant method. In the future, we will see, is there any development by doing these changes, or is there any downfall in this? Okay, so you can write these points. Consider the value of root in second iteration. Consider the value of root in second iteration using NR method. Consider the value of root in second iteration using NR method. A2 equal to A1 minus f of A1 by f dash of A1. Consider the value of root in second iteration using NR method. A2 equal to A1 minus f of A1 by f dash of A1. Where f dash of A1 is, slope of line joining the points, where f dash of A1 is slope of line joining the points A0 f of A0, comma A1 f of A1, where f dash of A1 is slope of line joining the points A0 f of A0, A1 f of A1. So after that you write these points, continue this, and after that you write this formula, generalized formula. Now with this we have finished all 4 iterative methods to solve algebraic and transcendental equations. Newton-Raphson method, bisection method, regular falsy method, and secant method. Now let us compare all these methods. That means I have one equation f of x equal to 0. This can be algebraic or transcendental. Now if I apply Newton-Raphson or bisection or regular falsy or secant method, so how the accuracy of the root will be particularly for that equation. So accuracy of the root is important for us. Okay. So let us know the importance, which method works very fast. Let us see. That can be decided in terms of order of convergence. So the next concept is order of convergence. Now let us see what this represents. See, yesterday, in one of the previous sessions, we have seen convergence in case of Newton-Raphson method. If xk plus 1 equal to xk for some k, then that is called condition for convergence, and in that case NR method converges to that repeated value. Now order of convergence, that means in which iteration you may reach convergence. So even if it is convergent, don't expect accuracy, but at least somehow we are expecting convergence. So if you expect convergence, in which iteration the method converges, right? Now basically order of convergence is nothing but the speed at which the iterative method converges to the root of an equation. Newton, basically it represents the speed. Order of convergence is nothing but, in simple word, it is a speed. The speed at which the iterative method converges to the root of an equation. Now let us compare with order of convergence by taking all methods. So we have a simpler tabular representation method, order of convergence. Now let us start with first one. So it is Newton-Raphson method. In case of Newton-Raphson method, the order of convergence is 2. If it is bisection method, it is 1. Even for Regla-Falsey method also, the order of convergence is 1. But in case of secant method, it is approximately 1.62. Now by looking at the table, one can easily understand that here the highest order of convergence is 2. That means accuracy is more in case of Newton-Raphson method. Here accuracy is only 50% when compared to Newton-Raphson method. Here it is almost 80%. See, this is somehow close to 2 but not 2. We had some changes in Newton-Raphson method. When we discuss the secant method, f dash of a1 is replaced by f of a1 minus f of a0 by a1 minus a0. Because of those modifications, the performance has been reduced from 2 to 1.62. Got this point? So therefore, this method has highest order of convergence. So, but in this case, in case of bisection and Regla-Falsey method, their performance is 50% less when compared to Newton-Raphson method. Now let me tell you what is exactly 2, 1, 1, 1.62. Suppose I have an equation f of x equal to 0. Suppose if I apply Newton-Raphson method to get the root of this equation, assume that I got convergence in 8 iterations. 8 iterations. In that case, if you apply either bisection method or Regla-Falsey method, you get convergence in 16 iterations. Now here the number of iterations is more when compared to Newton-Raphson method. So that means its performance is less. It is having highest speed. So the growth rate is very fast. But here growth rate is 50% less when compared to these two methods. So when you look at any equation f of x equal to 0, suppose when you apply Newton-Raphson method to solve that particular equation, if it takes 8 iterations to get the convergence, the same equation takes 16 iterations if it is to be solved either by Regla-Falsey method or bisection method. So number of iterations will be more. So here it is 8, here it is 16, double. That means here performance is 50% less. That's why the number of iterations will be double. So therefore, out of all these methods, this is the most effective method, right? So throughout the industry levels, people give priority only for Newton-Raphson method. So first write the definition of order of convergence. Order of convergence. It is defined as the speed at which the iterative method converges. It is defined as the speed at which the iterative method converges to the root of an equation. It is defined as the speed at which the iterative method converges to the root of an equation. Now you can have this tabular form. Now we start with an example. Let us apply Newton-Raphson or Regla-Falsey methods. Suppose I have an equation f of x equal to, for example, 2x minus 4. Now I need to get the root of this equation using NR method. Let us try to apply Newton-Raphson method. Now here the value of root in k plus 1 iteration is given by xk plus 1 equal to xk minus f of xk divided by f dash of xk. So this is nothing but xk minus f of xk is required. See, actually Newton-Raphson method, for Newton-Raphson method initial approximation is required. x0 is required. Now without this initial approximation, let us start with recurrence relation. Xk plus 1 is given by this. xk minus f of xk by f dash of xk. Now what will happen? This is xk minus f of xk is 2 into xk minus 4 by the derivative is this. So therefore this is 2xk minus 2xk plus 4 divided by 2. So 2xk minus 2xk will be cancelled. This is 2. Therefore here xk plus 1 equal to 2. This is a constant expression. So here initial approximation is not required. So that it is not required means whatever the initial approximation you take, always xk plus 1 becomes 2. What xk plus 1 represents? This is nothing but value of root in k plus 1 iteration. It is nothing but value of root in k plus 1 iteration. Now what is the root of this equation? Here when you take f of x equal to 0, this implies 2x minus 4 equal to 0. Therefore the root of this equation is 2. So which we got in the direct iteration itself. It is a constant expression. Therefore when you deal with polynomials of degree 1, this is a first order polynomial. So when you deal with first degree polynomials using NR method, they give accurate values even if you do not supply initial approximation. That means Newton-Raphson method gives 100% accurate results for all polynomials of degree 1 irrespective of initial approximation. Okay. So note these points. Example. Note. Newton-Raphson method gives accurate value. Newton-Raphson method gives accurate value for all first degree polynomials. Newton-Raphson method gives accurate value for all first degree polynomials irrespective of initial approximation x0. Newton-Raphson method gives accurate value for all first degree polynomials irrespective of initial approximation in single iteration only. In single iteration only. Because when you take k equal to 0, x1 itself 2 only. So in the first iteration itself you are getting directly 2. So Newton-Raphson method gives accurate value for all first degree polynomials irrespective of initial approximation in single iteration only. In single iteration. Now suppose if I take this f of x equal to 2x minus 4. If I apply bisection method, let us see how it reacts. Suppose for bisection method I need as an interval. So I need an interval a comma b where function takes opposite signs at the endpoints. Now let us see. Suppose if I take 1. For example, closed interval 1 comma 3. Now this is a polynomial function. It is continuous in this interval because all polynomials are continuous. Here f of 1 is 2 minus 4. It is minus 1 negative. F of this is a value. This is b. F of 3 is 2 into 3 6 minus 4. This is 2. So root lies in open interval 1 comma 3. So the value of root in first iteration is 1 plus 3 divided by 2. It is 2. So calculate f of x1, this is f of 2, you get 0. So 2 is a root of this equation. Therefore, even bisection method gives accurate value because its root is 2. It gives accurate value for all first degree polynomials in the iteration 1 itself. Even note down this example. Note, bisection method gives accurate value. Bisection method gives accurate value for all first degree polynomials in first iteration itself. Bisection method gives accurate value for all first degree polynomials in the first iteration itself. Right? So thank you so much. The session is over. In the next session, we discuss numerical differentiation.